let me recap what we've been doing so far, so that we can continue from where we left off in the previous session. We spoke about the meaning of a solution, and then I illustrated this using an example from with an ODE, which had, well, presumably a general solution and a particular solution, and then I said that we're actually solving the ODE plus a domain plus what I called auxiliary conditions. And these, well, auxiliary conditions usually are in the form of boundary conditions or initial conditions. And for the first order example that I briefly discussed, there's no distinction between the two, because you have to specify, to get all the undetermined constants in a general solution, you have to specify the value of y at some particular t naught, depending on where you choose it. It's either an initial condition or a boundary condition. And we saw that you don't really talk about solutions to ODEs per se themselves, because that is a very restrictive class of problems. In physical problems, usually you have an ODE, you have a domain, and you have initial or boundary conditions, right? In all physical conditions, in all physical situations where we encounter differential equations, and we'll see examples of that as we go along. So that's what we meant by a solution. A solution meant something that satisfied the ODE, was valid in a certain domain, and satisfied these initial boundary conditions. And then we discussed this idea of uniqueness of a solution, and this applied to all differential equations, irrespective of whether they're linear or non-linear. And it was guaranteed, at least for the initial value problem, the case where the auxiliary conditions are purely initial conditions for any higher order ODE, the uniqueness was guaranteed by what we called Picard's theorem. It said that when you have a system like this, and remember, the other thing, of course, that I have to mention is that if you have any general higher order ODE, we saw that you could reduce it to this form. Y bar is a column vector, f bar is also a column vector, and this looks presumably like a set of coupled non-linear first order differential equations. And you can do this just by making that substitution. You take, if you have, let's say, we worked out the example for a third order differential equation. If you take the first derivative, call that a different variable, second derivative another variable, let's say y2, y1, y2, and so on, you will get a column vector with y0, y1, y2, y3, and so on. And you can cast any general higher order nonlinear differential equation in this form. Okay, and please make sure you know how to do that. And Picard's theorem basically told us that when you have something that is of this form, and the right hand side is such that every component of this column vector is continuous, first of all, in the domain of interest, and it has in the vicinity of, let's say, the starting position. This applied to initial value problems where the auxiliary conditions were initial conditions, and in the vicinity of the initial conditions, we said this is what the initial conditions were like. Y0 bar is some constant vector, yeah, you could call it C bar, whatever, doesn't matter. In the vicinity of this point, we said that if the right hand side is continuous, the vicinity of this particular point, and if the derivatives dou f by dou yi, each of those components of f with respect to some component of y, if those derivatives exist in the vicinity of this point, neighborhood of this point, we use the phrase neighborhood. And similarly, if dou each of the f components by dou t exists in that neighborhood and is continuous, then the system, this initial value problem system, given that t belongs to t1, t0, t1, let's say, this initial value problem has a solution. The solution exists at least in the neighborhood of t0, y0 bar, and the solution is unique. Okay, so that's what Picard's theorem told us. We discussed that briefly. It turns out an easy theorem to state because the conditions are easy enough to state, but it's a very difficult theorem, or it's not a trivial theorem to prove. Okay, and So we won't talk about the proof, but this is sufficient. And like I said, for all practical cases that we will encounter, because theorem will guarantee that there is a solution. Okay, it's just for completeness we do this. And then we finally wanted to come to this question of how do we find a solution. And this is where that original hierarchy that I introduced sort of comes in handy. You started again, I'll write this down again. This is something that we probably have to internalize. Our first option, our first most ideal situation will be to get a closed form solution. And then the next one was quadrature or a series. That is the next option. If this fails, this is something you can do. And presumably this is better than a full experimental scheme that we discussed in the first session, because it still contains the physical parameters of interest. It's not obliterated, and you are not just mindlessly doing experiments to get information about the system. But it contains certainly less information than this. So you still need to numerically evaluate it, but you have the option. For example, if you have a series solution, we'll see when we get to it for second order systems, that if you have a series solution, you can in principle add more and more terms in the series, evaluate more and more terms numerically, and then get a solution to reasonable accuracy. So whatever accuracy you want, just include more terms and you will presumably reach that accuracy. Okay, so it's one step down, but not too bad. The next one was the qualitative business. This is where we'll look at solutions. Let's say what happens to solutions as t goes to infinity, or t goes to some other t2, and so on, right? So these are more qualitative things. We look at trajectories. I mentioned this idea about phase space. We'll talk about that. That will be the subject of today's discussion, and it helps answer some of these questions. So even though you don't get the value y for all t, presumably you will at least get something about the behavior, long-term behavior, because often in physical situations that is something that is of interest. So you have a system, let's say it's oscillating, doing something. You want to know if the oscillations are all going to grow with time, or they're going to die out with time, or is it going to continue oscillating the way it is, right? So questions like that you can answer using qualitative methods. And then the numerical schemes. Okay, so this was the hierarchy we introduced, the hierarchy of hopelessness. And we started off with the first order ODE system, and then I illustrated closed form solutions for the linear case. And I said that for a linear homogeneous, non-homogeneous, we saw how you could just derive the equation. For a homogeneous case, you just cross multiply and integrate. For the non-homogeneous case, you have to use this integrating factor that's often introduced, or you could just use this this technique that we introduced for getting that yp, right? If you remember, we discussed for a first order, we discussed this y equals yh linear. So this looks something like this: dy by dt plus p of t y plus q of t equals 0, and then this had these two parts of the solution, and then we discussed right at the end how you will get these two parts. The first part is the homogeneous part. This one solves the q of t equals 0 version of this. So that will just be dy by dt plus p of t y equals 0. And this one solves this. And we also saw that this is clearly just a differential equation. We've been talking about a system which contains an initial condition as well. So you can put, let's say, an initial condition that looks like this, only one of them, because you have only one derivative. And there's also something we discussed, why you would need values of the derivatives, values of the function specified at various points to complete the specification of a problem. And so if you put this type of situation, you will see, we saw this also, that the constant, the undetermined constant goes into y hat. The yp is completely determined. So the initial conditions that you put into the problem will basically go into determining the unknown constant and y hat. So all of this stuff we worked out. Please try it again by yourself. It's fairly standard algebra. I'm sure you've seen it before. If you haven't seen it before, again, it's a fairly straightforward procedure. For this, you solve YH from the homogeneous case, then you put Yp equals u of x YH of x. Put this back into the differential equation, and then you solve for u of x. Okay, and you will get that e to the power of minus integral p dx by p dt times whatever. I meant t, sorry. Okay. So you will get Yp if you know YH. And I mentioned that this is a better way to look at this problem, not the integrating factor. The integrating factor is something that's peculiar to a first order ODE. You can't use integrating factors as much for second order ODEs, which form the bulk of the ODEs that we will study. But this is a more general technique. So presumably, if you have this for a second order ODE, if I give you a homogeneous solution of the homogeneous equation, second order, we will see when we get to second order that you will have two homogeneous solutions that are linearly independent in some sense. Again, linear independence is probably something you have seen in the linear algebra part already. And it turns out you can use this scheme for a second order ODE as well. Okay? It's called method of variation of coefficients. But okay, for now it's just for illustrative case. So we've seen how to get closed form solution for a first order system. We've come to this quadrature. If you do this, you will be reduced to quadrature. You will get e to the power of minus integral p dt times integral q of t e to the power of integral p dt dt, whatever. So that reduces the problem to one of solving integrals. Even if the integrals are not solvable in closed form, they can at least be evaluated numerically, much easier than evaluating a differential equation, because there are very, very well established techniques for this. And so, okay, that's where we were. Now, very briefly, I introduced this idea right at the end. For nonlinear, you can do this, you can do this. For certain types of, for linear, you can do this and this. For certain types of nonlinear equations, you can still do this and this. They are of a very specific form, and the reason I'm not going to discuss them explicitly is because you seldom see them in physical applications. So they're more of an academic interest. But maybe I will put some of them out in the notes so that you just get some practice doing the integrals and so on. But from a practical point of view, the moment you go from linear to nonlinear, these two routes are kind of out, and so this is the only route you're left with. So today we'll talk about nonlinear ODEs, and especially we will develop some constructions in phase space, which I introduced right at the end, and then we will see how these constructions transform a problem. Now presumably this problem is one of calculus, right? You have to integrate and get a solution. So it's a calculus problem, but you'll see that here you've gone from a calculus problem to a geometry problem. So once an ODE becomes a geometric problem, it opens up a wide variety of tools that you can use to understand its behavior. And they're very interesting because they're a fundamentally different way of looking at the ODE. Okay, it's not something that people have likely seen before unless you've taken a course in nonlinear dynamics. So it's something that you have to get used to, because oftentimes it's really not a very good idea to run away and just start doing a numerical scheme with an ODE. That's probably not the best way to approach a problem first. The first step you will always do when you have a nonlinear system, again this hierarchy indicates that, is that you will try to get some information about the problem, some qualitative information, what are called fixed points and limit cycles and stable cycles and so on. And then once you have that information, it makes sense to do a numerical scheme to get the actual solution curve for a particular case. Okay, so that's the usual approach that you will follow in a nonlinear ODE. And if you remember from the first session, nonlinear ODEs are not, they're actually quite common. They in several situations they come up from nonlinear PDEs by some form of reduction or substitution or approximation and so on. And so these techniques are actually quite practically very useful. Okay, they're not just some random techniques that are there just for academic reason. Okay, so let's go back to the phase space construction that I started at the end of the previous session. The phase space is basically the set of all y that are possible. So, for a 1D system, this is just the real line, because a priori, I mean, this phase space, like I said, it's independent of the initial conditions. It depends only on the order of the ODE. It's independent of the right hand side. So, for example, if you have a first order ODE, the phase space is a line, real line, because all possible y's that can ever happen, that can ever come out of that ODE are basically real numbers. If you have a second order system, then it becomes a little bit more complicated. It's no longer a line, because now, if you remember, the second order system, if I just take, let me just call a general second order system, right? Autonomous, again, this is all for autonomous, non-linear autonomous. So, there is no explicit time dependence here. If there is explicit time dependence, you have to deal with it by increasing the dimension. We will look at that later on. So, if you have a second order system like this, remember what we said, that third order example that I worked out. If you just replace y is y0, y dy by dt is y1. I define new variables like this, and then I can just write down dy0 by dt equals y1, dy1 by dt, which is this g of y0 and y1. Okay, just like we did for the third order case. Now, if you do this and you come back and look at what phase space means in this context, here you had only one, where was that? I didn't even write it down. Dy by dt, this is a 1D case, autonomous. You had only one variable y, so you had the real line as the phase space. Now, you have two variables. Okay, and remember, we also discussed the fact that the initial conditions for the initial value problem will basically correspond to values of y0 and y1 at t equals t0, the beginning of the domain. So, you now have two lines that are basically going to vary independent of each other. That is the whole point. When we come to second order systems, this will be clearer. And so, in this case, it turns out phase space will become a plane. Two axes, it is a plane. Okay. Single axis, you get a line. Phase space in this case will be a plane. If you go to the third order system, the analogy just continues. There you will have three axes, y0, y1, y2, like we had last time, and that will give you a 3D space. So, phase space will become a 3D space, and fourth order will become 4D space, and so on. Okay. Good. So, for a 1D case, which is what we are focusing on right now, the phase space of the system is just a 1D ODE. The phase space is just a line going from minus infinity to plus infinity, and let us say your origin is here. That is the origin. Okay, this is y. Now, when you find a solution to this system, let us say I have an initial value problem. I have an initial value problem like this. When you find the solution of the system and you plot it in phase space, what that means is basically you are taking y solution is y of t given some t0, whatever, that is the initial condition, taken into the solution. So, assume that all the unknown constants are fixed by this. So, you have only one curve. Usually, when you think of a solution, you are thinking of something that looks like this. You have y, you have t, and you solve the ODE and you are going to get something, okay, looks like this. That is a solution. Yeah, so this is after solving the ODE. This is, let us say t0 is 0, we start from the origin, this is y0. So, this is the curve that obeys the initial condition, solves the differential equation, okay, for some complicated non-linear right hand side. Okay. Now, in this situation, if you want to plot the, we call this a trajectory, okay, this is a trajectory. And it gives the solution curve. So, y as a function of t is called a trajectory. Now, if you wanted to plot the trajectory in phase space. That's what we're going to do. You already see there is a problem. The problem is there's no t-axis. If I wanted to plot this trajectory here, there is no t-axis. This t-axis is not here, right? So if y equals y naught, this is y naught. Y naught is positive. This is the value of y naught. This is my value of y naught. Okay, that's y naught. Now, if I want to plot a trajectory here, what am I going to do? Well, I'll take a small time, let's say this time. I'll take another time, let's say this time. I'll take another one like this, and I'll just keep plotting. Right? This is the possible values of y that y can take, and the possible values of y are here. Okay. So let me make this trajectory a little bit better. Let's just assume it's monotonic for now, like this. Okay, this is the reason why I'll come to that at the end. Before the end of today's session, you will see why that is so. Okay. So then I go ahead and do this. I take t at some point t. Trajectory was initially here. It started here at t naught, t equals t naught 0, and it's going out like this. It's going like this, like this, like this, like this, like this. It's going out, presumably towards infinity. So I'm basically taking the projection of this on the y-axis, rotating it and keeping it down. That's my phase space, phase line in this case. Space is a line. Okay. Solution trajectory. Take that trajectory, project it onto the y-axis. Those are the values that y takes for the problem, and I'll rotate it and keep it like this. So this is the phase space, and this fellow is the trajectory. Simple enough to do. So now this you have presumably got from some complicated algebraic manipulation, some complicated integral. You have solved it, you have got that answer. This is purely geometric. Now notice we've gone from this calculus or algebra based scheme to a geometry based scheme, but in the process of doing that, our t identity is gone. So for instance, if I had a curve that looked like this, let me take a more concrete example. If I have two curves, y as a function of t, one goes like this, the other one goes like this, starting from the same initial location. Okay. So this solves one ODE, let me call it ODE1, and this solves ODE2. Two different ODEs, same initial condition, t equals 0, y equals y naught, and I get two different solution curves as a result. The domain is t presumably from 0 to infinity. And if I want to plot both these curves in phase space, they will look identical. Okay. Why is that? Well, what do I do for plotting it? I just take the projection of this over here. So I'll break this up, break this up, break this up, and both are, let's say, going off to infinity. So for the first curve, if I want to plot it in phase space like this, I'm going to get something that looks like this. This is y naught, and it starts at this point and then it goes off. Okay, this is the first one. Starts here and it's going off to infinity. The second curve will do exactly the same thing. The only difference is it will do it at a different time. So for example, this value, let's say y1, which is here, let's say this is y1. This first curve will reach y1 at an earlier t, this t, and the second one will reach y1 at a later t, this t. Okay. So these two solution curves are different. The two curves are different. They obey different ODs. They're completely different. But in phase space, they will be identical, right? Because it doesn't matter at what t you reach a point, just that you reach the point at some t. Okay. So in going from this calculus or algebra based picture to a geometric picture, you're gaining some advantage. We'll see what those advantages are, which help you deal with the problem a little bit better. But at the same time, you're losing this information about t. Okay, so whenever you do any analysis in phase space, you will see that exact t values corresponding to a certain y and exact locations on a particular trajectory are no longer recoverable. Okay, they're completely gone. That information is lost. So all you can do now is say, okay, what happens as t goes very large? T goes to plus infinity, what happens? Is this curve always going to go to plus infinity? Is this trajectory that is hugging this y-axis, is this phase space axis, is it always going to go off? Is it going to go at some point, turn around and come back? Is it going to go there and stop? Those are all questions you can now ask. Those are geometric questions. Okay, they are not algebraic questions, because you can use geometry to say under what conditions will, if I start, let's say I'm an ant, I'm sitting on a line like a closed line where you hang clothes, the ant going. Under what conditions can the ant go and come back? Purely geometric question. Under what conditions can the ant go and stop at some point? Yeah, that's another geometric question. Why will it do that? When will it do that? What are the conditions on the ODE that will make that happen, and so on? So those are all geometric questions. So this phase space gives us a nice playground to answer some of these geometric questions. Okay, that's the reason we're going to use it. And the same reasoning goes through for second order, third order, fourth order, and so on. When we come to second order systems, you will see that the analog just works just like in this case. Only difference now is, instead of having in a second order system, instead of having a line for the phase space, you will have a plane, like I mentioned, and so there are more things that can happen in a plane. Okay, so we'll see all that a little later on. Anyway, we'll continue with first order systems, and we'll talk about the types of things that can happen in phase space first, and then we'll systematically try and dissect them a little later on. So first order system, any first order system, this is the phase space, right? This goes from plus infinity minus infinity. That's the phase space. Now I'm going to make a construction that seemingly is a little counterintuitive, and it's not, but it could be a little misleading. So please stick with me. The construction I'm going to make is as follows. My ODE system is this: dy by dt equals f of y. This is my initial value problem. I've already set it up, and I want to see what happens in phase space. To do that, I will take the origin of phase space and superimpose on top of that the function, the right hand side function f. Okay, remember f is a function of y. Y is our phase space, axis. This is y, right? This is what y is, and f is a function of y. So I can plot f as a function of y like I would usually plot any function, f of x, f of t, whatever, just like this. I can plot f as a function of y on top of phase space itself. Okay. So for example, let's take an example. Let's take the most trivial example that looks like this. This is the linear first order ODE. You can write down the solution. Looks like this. Exponential kt. K is assumed to be positive. So solution is exponentially growing. It will just keep going to infinity. Now, for this situation, let me plot the right hand side. Right hand side is a linear function. F of y is ky. So I'm going to put f of y here, and notice I put a dashed line because, strictly speaking, it can be a little bit confusing, but just remember that I'm using this only as a guide. We'll soon stop doing this because once you go to higher dimensions, you can no longer plot stuff on top of phase space. It doesn't make any sense, and you will see why. Higher order equations. But for now, let's continue with this. Okay, so if I plot this, ky, k is positive, so the line is going to look like this. Straight line. Okay, this linear, trivial linear first order equation, straight line, f of y equals ky. Okay, this is okay. Now, in order to answer these long-term questions that I have been talking about, we need to have another construct in phase space, which are called fixed points. Okay. And what are fixed points? Fixed points are basically those values of y, which I am going to call y star, such that dy by dt at y star is 0. That is what a fixed point means. Okay. And since dy by dt is f of y, fixed points are basically f of y star equals 0. So, you take the right hand side function, you find the zeros of that function where the function reaches the value 0. Those are the fixed points, what are called the fixed points. And they are fixed points because if the system that you specified was such that your initial condition started exactly at the fixed point, so your y at t equals t naught was y star, let us say, for which f of y star is 0, then the derivative exactly at that point is 0. Okay. And if the derivative at that point is 0, derivative, if you think about it in this framework, let me just write this down. If you think about it in this framework, I have y as a function of t, and I have this is y naught. This presumably is a curve. Let me say the fixed point is here, this is y star. So, I am going to draw a horizontal line, y star, that is y equals y star. So, for any point on this line, y is equal to y star and f of y star is 0. Okay. If I give the initial condition y of t naught as being y star as opposed to y naught, which is here, this is y naught. If I give my initial condition as y star, solution curve will be like this. It won't change with time, or t, whatever t is. Okay. And the reason it won't change with t is because exactly at y equals y star, dy by dt is 0, because f of y star is 0, which means that t equals t naught plus delta. The solution is still at y equals y star, and f of y star is still 0, and dy by dt is still 0, and so on. Okay. So, to see this better, you can write, for example, this type of finite difference approximation. So, this at t equals t naught, this is delta y by delta t, let us say, and this is t naught and t naught, delta t is t naught plus delta t minus t naught. And this is equal to f of y star, which is 0. Okay. So, dy by dt delta y by delta t equals 0 in this approximation. So, the y at t naught plus delta t is the same as y at t naught, which is the same as y star. So, at delta t after t naught, you are still at y star, and the same argument continues. You are still at y star, f of y star is again 0. So, you do the same thing again for now t naught plus delta t, t naught plus 2 delta t, and t naught plus delta t, and again you will get delta y is equal to 0, and you will stay there. So, this curve will be your solution. So, it is a fixed point in the sense that if you start exactly at y star, you will stay there forever. Okay. So, that is what we mean by a fixed point. But algebraically, you can just define it like this. Good. Now, what are the fixed points for this system that we have here? Well, this is when f of y is ky is 0. That only happens when y equals 0. So, y star equals 0 is the only fixed point for a linear system, for a linear homogeneous system. Now, you can easily extend this idea, of course. You can say that if I had a non-homogeneous system, if I had not ky, but I had ky plus b, let us say, then you will still have only one fixed point, but the fixed point now will be where the right hand side is 0, that is minus b by k. And you can always change the coordinates. You define the new y, let us say some y tilde is y minus y star, that is y plus b by k. Put this back into the differential equation, and then For y tilde star, the fixed point for y tilde star will be again 0. So, there is only one fixed point, and we can, for all practical purposes, we can take that fixed point to coincide with the origin. Y star equals 0, origin of the phase space. Okay. Good. Okay. So, we redraw this phase space again. So, this is origin. So, for a linear system, for all practical purposes, I can take the fixed point as coinciding with the origin in phase space. So, this point is a fixed point. Okay. And you see that fixed points are unique because the fixed points are the only points at which, if you start exactly there, you will stay there forever, right. So, in that sense, fixed points are unique. Now, for linear, let me write that down as well. Linear system, one fixed point can be taken at, for a linear system. Okay, you can do that. Good. Now, what happens when the situation is non-linear? So, if you have a general f of y and you try to solve for f of y star equals 0, you can have multiple solutions. Just like, for example, if f of y was, let us say, a minus b y square, then f of y equals 0 will give you two solutions for y star. Okay. So, in general, for a non-linear system, you can have multiple fixed points. For a linear system, you have only one. Non-linear, you can have multiple, or none. Also, it depends on the physical situation. Now, why are fixed points useful? They're useful for the following reason. Let's go back to this example. Since we are convinced that b can be taken to be 0 by just shifting the origin in phase space. Let me just draw this. This is ky. Right, this is f of y. Slope of that line is k is positive. Now, try to understand why fixed points are interesting, why they are useful. Okay. Let us say this is my phase space and I am starting at this point close to a fixed point. It is close in the sense that it is not exactly at the fixed point, but at the same time it is not at infinity. Okay. So, it is somewhere near the fixed point at some finite distance. That is my initial condition. Okay, so, if I take as the initial condition, then I am going to start here and I want to ask the question, what happens to a trajectory if I start here? Okay, that is the question I am going to ask. And we can reason that out quite easily for a first order system. At this point, if you start exactly here, f of y gives you the sign of the derivative, it gives you the value of the derivative. So, the sign of f of y gives you the sign of the derivative. Okay. So, remember dy by dt is f of y. So, at y equals y naught, f of y is positive at y equals y naught. So, dy by dt is positive. That means y wants to increase with t, and okay, we will assume that t is generally increasing, right. That's okay, that is another assumption, standard, right, could be 0 to infinity, 0 to t, 0 to whatever. I am just writing t naught t1. So, dy by dt increases with increasing t. So, as you increase t from t naught towards t1, y will also increase. Okay. Why is that? Because let me say I start here at t equals t naught. F of y is positive, dy by dt is positive, so y should increase. So, this trajectory will start from here, it will go towards the right to some point. We do not know what that point is. That point will, where exactly it goes, at what particular value of t and so on, is all stuff that you will get only when you solve the differential equation. We have not done that. We are only looking at the physical picture in phase space. Well, good. Okay. So, it goes, let us say, to this point at some other arbitrary time, t naught plus some delta t, whatever. At this point, again, f of y is positive. So, again it will go to the right. It has to increase, so it will go to the right. and so on. You can continue this ad infinitum literally, and you will reach infinity eventually. Everywhere you go, it's positive. Everywhere you go, it's positive. And not only is it positive, it's more positive than before, so it will presumably go faster to infinity. But we don't know that information we can't get because we're not solving the system. If you solve the system, where was that? Got rid of it. If you solve the system, then you will get this, and from here that information is trivial, right? I mean, here you know it's going to infinity, it's going to rise for k positive as I keep increasing t. Let's say t1 is infinity, I'm going to keep increasing t, then the solution is just going to go, right? It's going to increase in value. But notice now we've got that information without solving. Okay, for a linear equation you can solve, it's fairly trivial. But if you have a nonlinear equation, you can do something analogous to this, which is what we're going to explore now. But this method is powerful because it tells you how the solution behaves as the independent variables increased towards t1, towards whatever. Okay. Now let's do one more thing. Okay, maybe we started on this side. Let's start on this side. Let me take y naught negative. Let me say y naught is here. Let's say what if y naught was negative? Okay, minus 3, minus 4, whatever. What happens then? Again, we'll assume that we don't know this exact solution. If you just look at phase space and you look at the sign of f, when you start here at t equals c naught, let's say I start here, dy by dt at t equals t naught is f of y here is negative. Okay. So because it's negative, f is going to reduce with increasing t, and as a result, if you started here, f is going to reduce, so it's going to go backwards like this. And then you come to a new location, it's more negative there, so it's going to go further, more negative, and so on. So it's going to go off towards minus infinity. And you can see this again from the initial condition. You put y of t is c e per kt, then if you put that initial condition, you will get c e to the power of 0, which is 1. So you'll get y naught e to the power of kt. If y naught is negative, it will go to negative infinity. If y naught is positive, it will go to positive infinity. Yeah, and we've got this without doing that stuff, without looking at the exact solution. It checks out to the exact solution. Now you see the problem has become geometric, like I keep saying, which is that without doing any calculus, you've been able to say what happens to the solution as t increases if you start close to a fixed point. Here, remember, we started close to a fixed point. Here the origin is the only fixed point for the linear system, so it's trivial. We'll do a non-trivial example in a minute. But if you start close to this, you're going to go off. If you start on the right, you're going to go off to plus infinity. If you start on the left, you're going to minus infinity. So in a sense, if somebody just gave you this phase space with only these trajectory arrows on it, they didn't give you any f, etc. If you could just get phase space with those trajectory arrows, you could look at a fixed point and say that trajectories that start close to the fixed point are going to go away from the fixed point. Okay, that's what happens. One case it goes to minus infinity, one case it goes to plus infinity. So you can now start being creative, imaginative a little bit, and say that okay, this fixed point, somehow trajectories don't want to go near the fixed point; they're repelled by the fixed point. Okay, that's a physical analogy you can make, right? I mean, why not? That's exactly what's going on here, right? If you look at this, you will not make that analogy because okay, you have a solution, you don't need that analogy. But from just the phase space picture, this is quite clear. Okay, good. Let's do a non-trivial example. It's also fairly trivial, but okay, it's certainly non-trivial than compared to that, it's non-trivial. Okay, so let's take, for example, let's take that. Let's take this f of y, this guy that I just wrote down there. So this is the OD dy by dt, and for all practical purposes, I'm going to set t naught equals 0 and t1 equals t1. Let's say this could be infinity as well, in which case it will be an open interval on the right hand side. Okay. And I'm going to give the initial condition y of 0, that's the initial condition, equals y naught again. y naught. Okay. Now let's go back to phase space again. Here you have minus infinity, plus infinity, origin, and dy by dt, the fixed points, which I am going to call FPs, fixed points, are f of y star equals 0. That gives you y star equals plus or minus root of a by b. Okay. So you notice now that there is now a constraint. So you don't. This gives you an example where there are two fixed points. But not only that, the existence of the fixed points depends on the signs of a and b. So if a and b are the opposite sign, the square root will become imaginary. Excuse me, and you will have no fixed points. So you will have no solutions to this equation. Okay. So to make things a little concrete, let's say a, b are both greater than 0. Okay. So what does this curve look like? Well, it looks, this is, let's say, minus square root of a by b, this is plus square root of a by b. These are the 2 points. Now you have the origin, which has nothing to do with a fixed point now, because that's not a solution of this equation, and you have 2 fixed points on either side symmetrically placed with respect to the origin. Okay. So let me plot this function f of y just like I did over there. I'm going to take f of y like this. So let's see, what will this look like? It will be a parabola. When y equals 0, it's positive. This is a. It's going to look like this. Okay, that's the parabola. That's what f of y looks like. And now things become non-trivial. Okay. If we did the same thing we did here, again this equation in principle can be solved. You can cross multiply, you can do partial fractions on one side, integrate the other side, you can do stuff, but we're not going to do it. Okay. We'll try to reason out the behavior of a solution just using the analog of what we did for the linear case. Okay. So let's see. If I started, assume for now y naught is positive, say it's here, this is y naught. This, if I started exactly here, at t equals 0, I am here, f is positive, so dy by dt is positive, so dy by dt positive, meaning as t increases, y is going to increase, so it's going to go like this to this point. So any point that's to the right of the origin is going to go, dy by dt is positive, so it's going to increase and it's going to go towards this fixed point. So there's one fixed point here, one fixed point here, and any point that you start here is going to go away from the origin towards this fixed point. What about on the left hand side? If y naught was negative, dy by dt is again positive, unlike that case where it was negative. Dy by dt or f of y is again positive, so again it's going to increase. So any point between these two fixed points, if you start anywhere between the two fixed points, you're always going to go towards the right side fixed point, and seemingly away from the left side fixed point. Okay. Now what happens when you do the opposite? So when you start, let's say on the right side of the right fixed point, let me say y naught, let's say is here. If this was my y naught, this distance was y naught, let's say initial condition was here, then at this point f of y is negative, dy by dt is negative, so y has to reduce, so it will come towards the left hand side. So wherever I start, I am always going to come towards the left if I start to the right of the second fixed point. Same thing applies here, the analogous thing applies here. If I start anywhere, let's say here or here, df by dt is f dy by dt is negative. Okay. So dy by dt is negative because f is negative. So any point I start here, I am going to go towards more negative, y reducing, becoming more negative or becoming less positive. Right? It's reducing. So it's going to go in the opposite direction. So if I just draw this phase space now, I am going to get I'm going to get something on a comma b. And that looks like this. I have two fixed points, one here, one here. Trajectories that are here are all seemingly being attracted by the fixed point. Everything is coming towards the fixed point, and trajectories that are close to this fixed point are seemingly repelled by this fixed point. Right? So this fixed point seems to be the analog of this. This fixed point seems to be the analog of this. If you had k negative, it would be like this. Right? So this seems to be the analog of that. But they are in pairs, like this. Good. Now just with this information, again I have not solved anything, I have only seen f, I have plotted f, which is okay, barely any work in this case, but just by looking at f, I have been able to say that the trajectories are going to behave like this in phase space. It's a very powerful capability. Now imagine if I gave you some arbitrary nonlinear f which had e to the power of y times tan hyperbolic of tan inverse of y, you could come up with that. I can do the same procedure, I can find out solutions. Now I will have to probably do some Newton-Raphson type method to get y star. Once I do that, I can then just plot f. I mean, I don't even need that actually, I just plot f as a function of y. I will see where it intersects the y axis, those will be the fixed points, and I can do the same reasoning as I did over here and then say close to which fixed point is it coming towards it and close to which fixed point is it being repelled. Right? So those are questions I can answer just by plotting f. Now, like I said, this plotting business is fine for a first order ODE because you have only y and you have only one f. Remember, if we had a second order ODE, we had this part, this guy. So if you had a second order ODE, this is a column vector, 2 entry column vector, this is also 2 entry column vector. So if you want to do the analog of this, first of all, your phase space will become a plane. Okay, we'll talk about that later. But in addition to that, if you wanted to plot the function itself, you now have two functions because this is a column vector 2. So now you have two functions that are a function of two variables. So you need a 4-dimensional plot if you want to do the analog of this for that case. Okay, so it's not feasible. So just drawing, looking at the sign is fine for a 1D system, but we want something a little bit more tractable, something you can generalize, just like we did for that linear system, yh, yp and so on, which was not needed but for the first order case, but we did it nonetheless with a view of it being useful for the second or higher order cases. We'll try to find an analogous expression for this now, okay, so that we can apply it to a second order case. It's geometry, but geometry expressed in the form of algebra. That's what we'll do next. But I hope this part is clear. The fact that these arrows are all drawn like this and this looks like it's repelling, this looks like it's attracting, all trajectories. Let me do one more example before we go further. So let me get into the second order system. Do one more example, which is that same as that, but with a equals 0. Okay, same, everything else same. So t belongs to 0 and y of. Okay, now what happens if I take the same phase space and I do this? This is y, this is f of y again. Now f of y is going to look like this. Now you have a problem. The problem is this. This obeys f of y equals 0, certainly does. Okay, this point. So it is a fixed point, after all, it is a fixed point. But now if you did this analogous argument, you will see if y naught was positive, let's say this is y naught, then f of y is negative, dy by dt is reducing. So if you start anywhere on this line to the right of the origin, you will always come towards the origin. Okay, all trajectories will come towards the origin. But now if you do, this is okay, so seemingly similar to this, okay, everything is coming towards the origin. But if you start to the left of the fixed point, over here, anywhere here, if that was your initial condition, then f is still negative. So dy by dt is still negative and it's still going to reduce. Okay, so irrespective of where you start, y is always going to reduce because f of y is always negative. It's never positive. So I hope we can make a distinction between this, this, and this. Okay. Now, these three types, I'm going to call them types of fixed points. Again, right now it probably seems like we're doing all this algebra for really nothing, but when I give out the assignment, you will see that these techniques are extremely powerful. They're very useful when you want to understand the behavior of nonlinear systems, and most systems that you will encounter are nonlinear to some degree or the other. Okay, so these techniques will be very useful when you do that. But for 1D case, there are three types of fixed points. The first is, I'm going to call this the, let me call this the unshaded fixed point. Open circle, unshaded. Okay, this is the shaded fixed point. I think they look significantly different now. Yeah. Okay, this is the unshaded fixed point, the shaded fixed point. So three types. First is this. Second is this. This guy repels all. This guy attracts all. All trajectories. That's what I mean by all. And then there is the third guy, which is this guy, which seems to repel from the left. So from the left, it's like open, like this. But from the right, it's attracting. So I'm going to half shade it, like this. Okay, so this is partly repel, attract. So these are the only three types of fixed points you can get. Why is that? Well, it depends. Of course, fixed points are a solution of this. So what other possibilities are there? You can take in any arbitrary function. This is again, let's say my phase space. This is y. Y. I can draw any arbitrary function, f of y. This could be any generally nonlinear function. It goes up, just whatever, and it's doing its stuff. Anytime f intersects the y-axis, that's when f of y star is 0. Okay. These are all fixed points, right? In the construction we've just made. And just by sheer fact that a function has to, if it goes from positive to negative, it has to go through a 0. Okay, that's a fundamental result from calculus. Just from that fact alone, you will see that, okay, this fixed point is of that type, this fixed point is of the other type, this fixed point is of this type, and so on. So you really cannot draw any other possibility for a one-dimensional system. So these are the only three types of fixed points you will get. Okay. They have names, of course. We'll see what those names mean in a minute. But first, we'll look a little bit more at this repelling, attracting business. Okay. So this guy repels all trajectories. Notice these are all trajectories. It doesn't matter if you're starting this close or this close or this close or whatever. If you're in the vicinity, you start in the vicinity, you're going to go away from it. This guy, same thing, but attracting. So if you start here or here or here, you're always going to eventually reach this fixed point. Okay. And this guy, likewise, if you start anywhere here, you're going to reach it. If you start anywhere here, you're going to get away. Partly repel, partly attract. Right. So this fellow that repels everything is called an unstable fixed point. Again, this is a term that we have to define because it's a maths course, of course, and you have to define stuff. Okay, so the one that repels is called an unstable fixed point. The one that attracts is called a stable fixed point, just by analogy, because it's stable because no matter where you start away from the fixed point, the system is always going to come eventually and reach the fixed point. Okay, and this fellow, the partly repelled, partly, is called a saddle point. Okay, so on one side it repels, one side it attracts. So you have three types of fixed points: stable fixed points, unstable fixed points, and saddles for a 1D system. 2D systems things become more interesting because the geometry is richer, but we'll get to the bridge eventually, and we'll figure out how to cross it at that point. Good. Now things are a little bit more interesting. I mean, you probably don't think about first order systems in this way, but this makes them a little bit more interesting. Before we go ahead, we have to define what this stability means. Again, I put it in quotes because I haven't defined what it is. So we'll define that, and then we will probably take off from here in the next session. So what do we mean by stability? Okay, I've just used those phrases seemingly just out of the blue. I just picked them out and I've just thrown them around cavalierly, but they have a very definite distinction, very definite definition. Sorry. Now it turns out there are two definitions you can give for stability. For the first order case, they're both equivalent. The first one is something called Lyapunov stability. Second one is something called absolute stability. I am defining these separately only in the view of eventually having to look at second order ODEs within this context. There will be a difference between these two when we talk about second order ODEs. But first order ODEs, they are both equivalent. What is Lyapunov stability? Well, notice stability is associated with a fixed point. It's not associated with the ODE, it's not associated with F. Well, indirectly it is, but it's not really a property of F per se, because F can have stable fixed points, unstable fixed points, and saddles. We drew that wiggly F a little while ago. So stability is always associated with a fixed point. Okay, that's an important thing to keep in mind. It's a property of a fixed point. So in Lyapunov stability, let's say I start y of t close to y star, so some fixed point, and what do I mean by stability of fixed points? So you start y of t close to y star, which means that the distance between y naught, the initial condition, and y star is smaller than some number. It's a very small number. Delta is a small positive number. So it's at close to y star. That's where the trajectory starts. If I do that, and if this happens, and this implies, if it implies that y of t minus y star lesser than some other small number epsilon for all t within the domain of interest, then the y star is Lyapunov stable. Okay. Again, I start very close to y star, the distance away from y star being modulated by delta. If I do that, and if that results, if this resulting system, if I figure out where it's going and so on, and I see that for all t within the domain, y of t is in the vicinity of y star, now in the vicinity being defined by epsilon, then that means that the y star is Lyapunov stable. Okay, and this is again a property of a fixed point, so you have to check this for every single y star. So for instance, this fellow, if you start close to it, we saw that it repelled, so it was not Lyapunov stable. This guy, if you start very close to it, everything comes towards y star, so you're always in the vicinity of this point. So this one is Lyapunov stable. Okay, and this one is not, because you start on the right, you will come towards it. If you start on the left, you will not. So it violates this condition. This does not assume that y naught is on the right side of y star or left side of y star. Okay, it's only the distance. Okay, so that's what we mean by Lyapunov stable fixed point. Now the absolute stable fixed point is simpler. So this happens when the domain is, let's say, 0 and infinity. That's our domain. So you start at 0 and you go all the way to infinity. And this is not such a restriction because you can take any domain of this form, and you can suitably rescale it and make it such that it becomes like this. Okay, and since the system is autonomous, the differential equation is not changed. It will only get a factor that goes in, some scaling factor, right? So this is a general equivalent of this. It doesn't matter. You can always go from this to this for an autonomous system with a trivial change of definition of T. Okay. So this idea of absolute stability is the following. If I start close, again close, let's say similarly to this, delta is a small number, so I am starting very close to y star. Then as t goes to infinity, if y of t reaches y star, then y star is absolutely stable. Okay, so if there's a difference between these, so this says that it's always in the vicinity of y star for all t. This one goes one step further and says as t goes to infinity, it will eventually come and reach y star. Okay, y star is the limiting point of this. So then y star is an absolutely stable point. Okay, good. I'll just make one last comment about why I said for 1D systems, Lyapunov and absolute stability is the same thing, and I'll also use that to say something about this effect of geometry on the physical behavior of a system. So let's take our phase space again. Let's assume there is one fixed point here, and let's say it's unstable. Okay. Now let's do a sort of thought experiment. This again, seemingly we're going far and far away from a pure mathematics setting. It's an alternate way to look at the subject. Of course, it's, I think, very insightful. But let's say this is my phase space, and I'm an ant, small ant, and the ant is going on this line. The direction that the ant has to go in is determined by what? It's determined by f of y. This gives direction of motion of ant. So this is the ant, this is the, presumably ant has some antennae thingies, whatever, and then it has legs, and ant is going. Okay, it's walking away. So if this is an unstable fixed point, then f of y is such that the ant will always go away. The motion of the ant, let's say, represents the trajectory that we're going to take. Okay, that the system is going to follow. The trajectory in phase space is represented by the motion of the ant. Okay, that's all. So now we don't have to worry about the differential equation. We'll toss it out. We don't care about the trajectory. We're only worried about the ant and how it's moving. Now, if the ant is on the right hand side, then f presumably is like this, of some form. It's like this. So f is increasing. So the ant is going forward towards positive infinity. Okay. First of all, under no circumstance can the ant ever go in one direction and then change its mind and come back. Why is that? Well, because f of y has a fixed sign. Of course, f of y cannot have two signs on this side. Remember, it's a good function, a single valued function. So f of y is always positive on this side. If it ever has to become negative, then it has to cross the y axis. It has to cross the phase space again, right? So the only time f can become negative is if it comes down like this and it crosses this point again. There's no other option. If it didn't do this, it will just keep being positive. It could be less positive than it was before. So it could be, for example, if it never became negative, it could be like this, but it's always positive. It could go down a little bit, have some hill and valley and so on, but it's always positive. which means the ant is always going in this direction. Now the hill and valley will tell you, okay, it's going to go and then it's going to slow down a little bit suddenly and it's going to go faster and it's going to slow down and so on. Okay, that's what it's doing. But it's always going in this direction. Okay. Now notice that if the ant ever wanted to come back, it's going in this direction, if ever wanted to come back, the only time it can do that possibly is if f changes sign. Okay, because sign of f is telling the ant to go, positive f tells the ant to go positive right direction, negative f will tell the ant to come back. So if it wants to come back, let's say it stops here and this point, I'm going to call it an x, ant has come here, it now decides, okay, I have to go back, okay, this is too much, I want to go back, and it returns like this. That means that at this point, f was originally positive, but either the ant is disobeying f or f has changed its sign. Okay, we'll assume that the ant never disobeys f. That means f should have changed sign, and f cannot change sign again unless there is a fixed point between. Okay, so that's the first thing to remember. So ant cannot retrace path. It cannot come back. Yeah, it has to go. That's a very powerful result. Okay, and I'll show you why that's a powerful result in a minute. So if it cannot retrace its path, that means the ant cannot return to original position. To let's say y naught, wherever it started from. Let's say it started here. This is y naught. And cannot come back to y naught ever. Not possible. Because if it has to come back to y naught, at some point it should have be going this way, it has to come back this way, and again that will mean that f has two signs at the same value of y, which is not possible. So ant cannot come back, which means a first order ODE system, first order, cannot have any oscillatory solutions. No oscillations. Okay, you cannot have a first order system that gives you a periodic oscillatory solution. It's not possible at all. Autonomous, of course, this is autonomous, but yes, nonetheless. So you cannot, for example, cook up some f of y that's nonlinear enough that is going to make stuff oscillate. No, cannot happen. Why can it not happen? Because you have a line. If you have, instead of line, if you had a plane, then if the ant started here, it will be going like this. Suddenly it can decide to take a left turn, take another left turn, take another left turn, come back to its original position. That's possible if it's a plane, but it's not a plane, it's a line. So the ant has no hope. Okay. So in a 2D system where phase space becomes a plane, you can start having oscillations, right? Presumably you can do this stuff, and you can go around, come back to the original position. So you have oscillations in 2D systems. We know that spring mass systems, all of that stuff that we've studied, they're all 2D systems for a reason. Okay, because if there were 1D systems, springs will not oscillate and there will be no vibrations and so on. Okay, good. That's point number 1 about the ant. Point number 2. Okay, let me come to point number 2. Let me write it down here. So point number 2, just sort of extension of this idea. If the ant starts here and it's going like this, just like here, like I have here, if it's going, I'll get rid of this, we don't need this. It looks more like a cockroach than an ant, but yeah, okay. That's an ant. Okay, if the ant starts there and it's going forward, then because there is no possibility for the ant to retrace, it has to only keep going. It has to only keep going until either it stops or it reaches infinity. There is no other possibility. Okay, it can't come back. Remember, this is a 1D phase space, it's a line, so you either go this way or you go this way or you don't go anywhere, you stay stationary. If the ant becomes stationary, that means it's reached a fixed point. Okay, that's the only time it will become stationary, when it reaches a fixed point. It could slow down, it could speed up, but it's still going in the same direction until it reaches a fixed point or it reaches infinity. Okay, which means that if there was a fixed point here, let's say this is my fixed point. If the ant is going in that direction, it's eventually going to reach the fixed point. Eventually it will reach here. If it started anywhere in the vicinity of this was my ant. If it started in the vicinity of this fixed point, it's eventually going to reach the fixed point. It will always be in the vicinity of this fixed point, but more specifically, it will always reach the fixed point as t goes to infinity. It might reach it asymptotically, but it will reach it. It has nowhere else to go. Okay, 1D system, it has nowhere else to go. There's nothing else to do. In a 2D system, if the space phase place was a plane, you could imagine the ant is coming like this, and suddenly it decides to take a turn, it'll go left and go far away. That's possible. 1D, it's not possible. That's why in 1D systems, Lyapunov stability, which means that the ant is always in the vicinity of this, or the trajectory now, the trajectory is what the ant represented. Trajectory is in the vicinity of the fixed point, is the same as eventually reaching the fixed point, because as t goes to infinity, there's nothing else to do. Okay, so that's what we mean by stability. So Lyapunov equals absolute. Okay, and that's basically a property, and all of these are just geometric properties. There's nothing, we haven't solved any integrals, we haven't inverted any differential equation, we haven't done anything fancy like that, and we've only used geometry to say what is going to happen, and we see that this is the situation. Okay, good. Now the next question we can ask, which is what we will start off with in the next session, is okay, given that there are these three types of fixed points, stable, unstable and saddle, and stable, unstable being defined in this way, all trajectories eventually reach there, all trajectories eventually get out, or some trajectories reach, some trajectories don't, depending on which side of the fixed point you start. Given these characteristics of fixed points, can we envisage a situation where one fixed point goes from being stable to unstable? Okay, I mean, why would we care about this? Well, this is probably the central reason why nonlinear dynamics is useful, and it's also the central reason why people study this subject. It's called the theory of bifurcations. I'll talk about that briefly, but just to give you an analogy, take for example flow in a pipe. So you have a cylindrical pipe, you have fluid coming in, it's going, let's say you have a big pipeline and then it's going from, I don't know, from Madhya Pradesh to Gujarat or something, and you're pushing fluid through the pipe. Now at some critical value of some dimensionless number, some number, let's say some combination of the viscosity and the diameter of the pipe and the density and so on, the flow in the pipe goes from being smooth laminar flow to all of a sudden becoming unstable, and you want to know when that happens. Okay, so you're tweaking one parameter, this is okay, Reynolds number, whatever, you're tweaking one parameter in the problem, and at some point the solution that you had, the steady state solution, remember I said going from PD to ODE one way was to just look at a steady state solution. The steady state solution is going from something that is fixed, some constant flow pattern, to suddenly something that is oscillating, something that's doing weird stuff. So presumably the fixed point of that system has now suddenly changed from being a stable fixed point to an unstable fixed point. Why is that? Well, if it was always a stable fixed point, then any initial conditions that you have will tend to converge the solution towards that fixed point, and so irrespective of what changes locally, there is some change, there is some roughness, there is whatever in the pipe, whatever those changes are, whatever y naught is. I'm just making a loose analogy. It turns out the analogy can be made quantitative, we won't go into that, but no matter what that y naught is where you're starting, the fixed point being stable, let's say fixed point represents some laminar flow fixed point, will always attract all trajectories towards it, so you will always see the same type of laminar flow. Okay, but the moment for some combination of parameters the fixed point becomes unstable, then even the smallest y naught disturbance will throw your fluid field away from laminar. Okay, so it will start doing, you'll have vortices, you will have local circulations and so on. Just loosely from an analogy point of view. So the stability of systems, you will see this being applied multiple times repeatedly. This idea of trying to understand when a fixed point changes its stability, under what conditions, and what is the mechanism for that to happen. It turns out this is also a question that you can answer geometrically, just purely based on your imagination. You can imagine what type of things can happen from a geometric point of view, and you can use that to guide the analysis of what types of stability change can occur. Okay, so that's what we're going to do in the next session.